So let's start our lecture. Okay, so you remember we covered syntax, we covered lots of different things. By the way, also the lambda, if you remember the lambda calculus, we didn't go through it. And the tutorial on Friday is going to cover a few pages of the slides if you didn't cover it on your own. So try to cover it, try to attend the tutorial. He fixed the issue that he has, so you can able to see now the links on Zoom from the Zoom link on Brightspace. So we said that now we covered syntax, we covered grammars, we want to move to the semantic analyzer. We want to understand now what is semantics. First of all, few things that you're going to, if you're reading the book, for example, if you're looking online for sources, we mentioned that semantics means meaning, right? Not the syntax. But when you read the word static, okay, why this is not. Okay, 1 second. Okay, it worked. So when you're reading the word static semantics, no, this is not, we're not talking about meaning here. Static semantics is just a way to explain the rules that govern contextual constraint, and it's related mainly to attribute grammars. So when you read static semantics, we're not talking about the meaning, okay? When we're talking about the meaning, you're going to hear the word formal semantics or dynamic semantics. So formal and dynamic, this is what we mean when we say meaning of the program. But I just put this here just for you if you're reading online and you pass by the static semantics. Okay. So now we know that it's not as easy as the syntax thing when it comes to defining semantics, right? And it's agreeing upon that there is no single widely acceptable notation or formalism for describing semantics, okay? Why is this? Because if we want to understand program behavior as programmer, we may apply what? A trial and error. Why? Do you remember when we started? For you, for example, if you want to understand something, if you want to understand a for loop for a newly language, what are you going to try to do if you don't have a manual? You're going to start doing a trial and error. Okay, let me check for this, do that, how it's going to work, right? So usually this is thing, what did we mention about it? Can we depend on this trial and error? It's going to take us years to figure out the meaning of the language if we just want to do the trial and error thing. Correct? Okay. So what about, these are us as programmers. What about the people who are developing the compiler, right? Because technically this method, we're assuming here that you have the compiler, right? So you're using the compiler to understand this language. Okay, so let's go one step deeper. What about the people who want to write this compiler? How can they understand semantics? Because they cannot do trial and error in this case. What will happen? Usually, let's say they want to read the English manual describing this language, right? Like someone wrote a manual in English. Okay, for loops mean this, while loop mean that, this statement mean this. Do we think this is actually dependable? What do you think? If let's say I give you now an English manual about a specific programming language, I give also Michael one, what's going to happen?
So suppose you run context, but you'd have varying answers.
Exactly. Why you're going to have varying answers? Because maybe you and Michael read the same English thing, but what? They interpreted it in a different way. So I understood from this sentence this, he understood from this sentence that. So we'll end up having someone here in Canada reading the same manual, while someone in the US reading the same manual, doing two different compilers that do a bit different than each other. So it's not very practical to do this, correct? So that's why, actually, and we said that's a potential issue of two programmers may interpret the language differently. So that's why we need a solution for this. And we need something called formal semantics. So we want this meaning, it's true it's a meaning, but we want it to at least to be a bit formal. So the same way we have rules for the syntax, we want to have some rules for the semantics, for the meaning. But it's going to be much harder than the syntax, because the syntax, you can just say, for example, if you don't have a semicolon, there's a syntax error. Semantics is a bit more complicated, right? So we're going to actually study some of the formal semantics that is used to describe the meaning of languages. So we'll start with what is formal semantics. So actually, formal semantics is a mathematical specification of the meaning of the program, guys. Okay, so that's what you want to think about. It's a way that we're using some math stuff to describe the meaning. Now, if you read the word dynamic semantics, it's part of the formal semantics. So formal semantics is just a broader terminology. Okay, the dynamic semantics is the same thing. We're talking about the meaning, but it's more like what happens when the program runs. So I just put both terminology just in case you're reading online something and you see dynamic or formal. Both of them were referring to actually the meaning of the program. So now, why do we need a methodology and notation for semantics, guys? Why do we need that? Yeah. Why do we need that? Because, of course, we said programmers will need to know what statements mean. So that's the first thing. So a methodology is good for the programmers, and also for who? For compilers, as we mentioned. Let's say a compiler developer wants to write a compiler, it needs also to know. Now, the most important one is not just this. If I ask you, I want you to prove for me if this language semantics is correct. If it's just based on your own interpretation, it's to become what? Philosophy things. Like everyone is going to give a philosophical answer. No, we want like something that we can say, okay, we can prove there is something called correctness proof. So we follow these formal rules of semantics, and then we can say, you know what? Check, check, check. This is correct. Okay, so correctness proof is very important. That's why we need methodology. And compiler generator is another one. Why? What if we can write a program that will generate a compiler for me? So I don't have to actually write the compiler from scratch, for example. So I need specific rules, because when it comes to machine, it needs to follow specific rules, right? It's not like you thinking about the reasoning and writing it yourself. So if we have a formal way, a methodology, we're able to also create something called compiler generators. And then also, of course, ambiguity is something very important for us. If we have these rules, we're able to found them. Now, what is the aim of formal semantics? Is to actually apply this methodology, okay, through formal semantics. So the formal semantics will give us precise specification of the behavior of the correct program. Now, here, guys, when we mentioned a correct program, are we talking about syntax or semantic? Yeah. So you start with syntax and then you say both. Okay. Wants to say syntax only, semantics only, or both? Alp. Syntax. Okay.
Semantics or both?
Semantics or both. Why do you think syntax, Alp?
I think of like based off the actual understanding of it, for a program to be correct, it needs to be able to be written properly so that it can pass through.
Okay. You have a different answer?
Well, maybe just the semantics.
Okay, because we're talking about formal semantics. So technically, guys, if we want to combine all of your answers, what can we say? What is a compiler? We said start with lexical analyzer, right? And then what? It feeds to a syntax analyzer, and then the semantic analyzer, correct? So technically, for a program to be correct, it has to have everything together. Now, at this point here, we're covering this one. We're covering semantics. That means I shouldn't worry about anything before that. So when I mean the behavior of the correct programs, I should assume, if I'm personally, I'm a semantic analyzer now, I should trust the process and say, you know what, anything is passed to me is synthetically correct because the syntax analyzer covered the syntax error. So I'm assuming that I'm receiving a correct program when it comes to syntax. Okay, and now as a semantic analyzer, I want to make sure that what this program is also correct when it comes to the semantics. So we can say both. We can say syntax like Alp said, but feeding to now, and then we can say semantic because we're covering it now. Did we get the point? Okay, so the most important thing that when it comes to formal semantics, we don't care about the junk. So for example, let's say I'm using C, and in C, I'm writing something that doesn't have, it's missing the semicolon. I'm not going to even analyze, check the semantics for it, the meaning, because it's not even syntax correct. So I'm not going to waste my time. But if it's synthetically correct, now I can move to understanding it and understand the meaning of this statement. Good? Okay. Another thing, the aim of the formal semantic is to give me a framework for reasoning. Why? Because we said if two people are just reading English manuals, the reasoning will be based on what they are understanding. But no, I want a specific framework that I can follow to able to reason better, reason from a scientific, more mathematical point of view, for example. So now, who needs to reason about programs? The programmer, for example. Okay, so you as a programmer, let's say you're writing your code. So what are you going to check? Does this code do what I want to do, for example? Hopefully, because you're writing it. But most importantly, how do we reason usually? We say, is replacing it with better code okay or not? Right? So let's say I gave you a template, like now we're saying, for example, I gave you a skeleton template for the assignment. One of the things that when you're reasoning about this assignment, you're going to ask yourself, what if I just replace this function? Maybe I don't have to follow it, for example, right? So we ask ourselves this. So how can we decide if we're able to do this or not? How can we decide? So let's take this as an example. Let's say I have a program that's telling me x equal x plus 1 and then x equal x plus 1. You came, you read this, and you said, I can just maybe replace these two by x equal x plus 2. I will optimize this code, correct? What do you think? Can you optimize it like that? What's your opinion on this? There's no trick questions. We're just like brainstorming together. I want to just like think like, how would you tackle this? You will optimize it? Okay. Yes.
I mean, it depends on the use. Maybe you do want an x plus 1. You may want x plus 2 as well, but.
So technically here, so what I mean is that, let's say the program is this, okay? So this program one, it say x equal x plus 1, and then x equal x plus 1 again. And this is not good pen. Okay, I'm saying, okay, you're looking at this one and you're saying is what? They are doing the same thing, for example. Let's say I have here x equal 1. So here I have 1 plus 1. Then I'll have here what? 2 plus 1 is going to at the end equal 3. So why can't I just say x equal x plus 2 right away? So if x equal 1, then it's going to end up with 3 also. So you're thinking like this. So Benjamin is saying yes. You're saying
If that's the only use of the program.
if that's not. So you're saying it depends on the program that I'm writing, for example. Okay, Michael.
Behavior of both programs ends up with the same thing that you want to do. If it gives the same behavior for both, then yeah, you could optimize it. If it doesn't give the same like output, then probably not.
Okay, very good. So technically here, actually, yes. So it's going to depend on not the program that you're writing, more than on the language itself that you defined. Why? Let's say the language that you're using doesn't use what's called like parallelism, so multi-threading. In this case, the only way for the language is to go like this, right? So even if it does this, this is going to end by 3, this is going to end by 3, so it's the same thing. So yes, I can optimize. But what if your language supports parallelism? What do we mean by parallelism? Sometimes, let's say you're doing x equal x plus 1, and x was originally equal to 1. So you started by this 1 plus 1 equal 2, correct? So technically now here you're going to put 2, but if you support parallelism, that means on another thread, x can get updated to 10 right away out of nowhere in the same time. So let's say you executed this line and then this line was executed. And then now the next one is what? It's 10 plus 1, not 1 plus 1. In this case, you cannot do this because you're supporting parallelism. Some languages do this. So that means to answer this, you need to look at the formal semantics that you have in this language. Does this language support this? Doesn't support that? So you cannot just decide out of nowhere. Unless you know the language. Let's say, okay, you're using C, and you know C, I can do that. You're using Java, you know that Java, that's okay to do this. For example, do you remember the mutable, immutable stuff? Some languages, you're not going to care if you're doing this, but some other language, no, you have to, for example, think about mutability. Some other things like C, you have to be careful about the pointers, that, you know what I mean? So it depends on the language. So that's why we actually need to know formal semantics. Good so far? Okay. So let's take an overview of semantics approaches. So the most popular ones are operational semantics, which describes how a program executes step by step. We're going to talk about it. And then we have the denotational semantics. It provides mathematical meaning of programs, mostly based on functions. And then we have the axiomatic semantics, which focuses on proving correctness, but with something called pre and post conditions. We're going to talk about them a bit more. Now, when it comes to the operational semantics, I'm going to describe it a bit. Denotational semantics, we're going to actually just mention what it does, but we're not going to go and explain it. We're going to skip it because it's mainly focused on, it's used by functional paradigm. And now we're focusing on what? On the imperative languages. We're going, at the end of this course, we're going to also maybe have one lecture about functional and another one about logical paradigms, but you already covered these in programming paradigms, right? So that's why now we're going to focus on the axiomatic semantics. So I'm going to give many examples on this one, how to solve them. On the tutorial, we're going to also solve examples, and in the midterm, for example, we're going to use the axiomatic semantics when it comes to solving actual examples. But you still need to know what operational mean, what denotational means. Okay, guys? Yes. Yes. So these are the types of formal semantics. For example, if I'm telling you, I want you to write a formal semantic for this one, you're going to ask me, okay, which method do you want? You want the operational one, the denotational one, or the axiomatic semantics? So the operational semantics, guys, for you, what you care about is what? It's that it explains how program state changes step by step during the execution. So the way that this is written, the rules, is that let's say I have a for this condition, do this statement. So it's going to say, okay, the word for means this, the do mean that, like, so it's going to go step by step on each line of the code and check what is the state of this. So it's step by step thing. Now, because it's step by step thing, it's going to be a bit hard to do it on the actual machine code or hardware. We're going to see why. So usually, the most popular approach for the operational semantics, they use a virtual machine to do so. When to choose this operational semantics, usually it's chosen mostly when you want to describe a specific language step by step. For example, if you're designing an interpreter or a virtual machine, if you're designing it and you want to explain it for someone, let's say you want to put it in a manual, you can, for example, do the step by step and someone can read it. Also, it's used a lot in language manuals, as I said, and for teaching and learning. So let's take a bit deeper look on the operational semantics. So we said it's a step by step, but we can construct it in two ways. Either the real machine. Now, when we say real machine, real hardware, we're talking about something called pure interpreter. Do you remember in the first lecture, we mentioned there is 3 ways? to translate something. So how are we going to talk with the machine? So I'm speaking a specific language, and this machine, let's say it understands 0 and 1s, for example, or something even less than that. So how can I usually, how the machine would understand your programming language? What did we mention? Through what? Yes? Exactly, we mentioned it's either through compiler, right? Or we said there's something called pure interpreter. It's just like the pure, and then we said something like hybrid. Who does hybrid thing? Which is no, like the hybrid like thing, which is a mix between a compiler and an interpreter. Maybe, yeah, but more popular one. I don't know about the Perl, but Java, virtual machine. You remember we said there is the JVM. You always have to install the JVM, right? You have to always Java virtual machine. You have to install it to be able to use. That means it's a mix of both. So when you hear this word idealized machine, it doesn't mean a perfect new MacBook that you have and you think it's ideal and I'm on the top of the world. No. Idealized machine means what? It's a virtual machine. We call it idealized or ideal because if you're building a virtual machine, you're going to give it a constant things or consistent stuff that you don't have to worry about the operating system or the hardware or the CPU or the GPU because it's a virtual machine. So there is lots of things are consistent and what constant, for example, time. So you don't have to worry about things. So it's like as if it's an ideal space. Okay. Now, if I want to go with the pure interpreters thing, what are the problems for me if I'm writing my operational semantics directly on the going to the machine using pure? What would some of the problems that I will have? Because remember, operational semantics writes step by step. So every single thing that's happening, it's writing it. So what would some problems with this method will come up for you guys? Think about it. Let's say Benjamin is using a MacBook and someone else here who loves using Linux, who use Ubuntu.
Like issue when it comes to
For what? Issue with what?
different operating system. So it might not.
So that's something very good. That means, let's say, someone is writing the operation semantics directly on a MacBook or on a specific hardware. So it's going to take into consideration anything related to this specific hardware while you're writing it. So that means if I'm writing it step by step, and I gave it to, let's say, Benjamin to apply it somewhere else, he'll have to apply it on the same exact what? Operating system or the same exact hardware, because these rules got affected with the environment. Okay, so that's actually one of the problems that we have when we want to write it on pure interpreter. That's why interpretation depends on specific hardware and operating system, for example, make it hard to understand the program's behavior. Why it's hard? Because is this behavior that's coming, is it pure from the language? Or is this because, for example, maybe there's something related to the operating system? Correct? So that's why a semantic definition done this way would be available only to those with an identical configured computer. So what is a better approach to do that? Usually doing the idealized machine, which is the virtual machine. To do that, we need to simulate the program using an idealized machine instead of real hardware. How can we do this? Usually, we divide it into two steps: translation and what? And simulation. So the first thing, we're translating our, let's say, Java code into what? Into something. And then we want to simulate this. So let's take a look on that. Because we said, for example, one of the most famous examples is Java virtual machine. So what's happening actually here? Translation. We're translating the Java code into bytecodes. But when we do this, Are these byte codes connected to any specific hardware? No, it doesn't matter. That's why when we do the simulation on the virtual machine, which is the Java virtual machine, it's going to run no problem with any of these, Windows, Linux, Mac. It doesn't matter because the code, where is the code running for you? On the virtual machine itself. Okay, so this is one of the, just for you, this example for you to understand what we mean by virtual machine. Okay, now let's move to denotational semantics. As we said, we're only just going to talk in general about it. So it describes the mathematical meaning of programs, and it's solidly based on function theory. So when it comes to functional languages, functional programming languages, they are usually described with the denotational semantics. Okay, so that's the only thing for this course that I want you to know about this thing. We're not going to cover it because we cannot cover every single semantics. It will take us forever. So we're going to only focus on the axiomatic semantics. What is the axiomatic semantics? It focuses on proving program correctness using logical assertions. So this word assertion is important for us. It uses the OR logic, I hope I'm pronouncing it right, with precondition and post conditions. So here, instead of going step by step, we're going to say, do you know, for example, let's say this statement, I just give you with it a post condition and a precondition. That's it. Okay? We're going to check what it means. Useful for verifying that the program meets specification. Now, this is a summary table that I left for you, just for you to take a look about the difference between them. And then now we're going to move to the actual examples. We're going to solve it together with the semantic assertions. Before we do that, we're going to wake you up with a WOO clap. So let's turn. Okay. Settings, that's fine. And then display. Okay. Okay, so let's do this. So now these WOO clap, these questions are going to be a summary for everything I just explained now on the slides. Okay, so this hopefully it should stick in your mind, but that doesn't mean that you can always sleep during the slides and then just learn everything with the WOO clap. Everyone is in? Anyone still needs more time? So let's start. What is static semantics? Is it the meaning of a program, or it's not directly related to the meaning? Like everyone to participate? Exactly. So it's not related to the meeting. Whenever you have the static before semantics, don't just go right away to the, okay, semantics mean meanings. Okay. So what is the best way to understand the meaning of a language, guys? If I want to understand the meaning of a language, should I do the trial and error one that I'm going to try it, or through a precise method like formal semantics, which ensures consistency? Exactly. Why it's not a good idea to let a compiler, developer, or interpret the semantics of a language by reading its English description from the manual? Why would it not be? Of course, because we said two developers can interpret something differently because they are just based on their understanding of this. What does this mean? Now, what is the definition of formal and what is the definition of dynamic semantics? First, we said both of them, formal semantics and dynamic semantics, both of them, they are referring to the meaning of the language, right? Okay. So which one refers to the mathematical specification of the meaning, and which one focuses on describing the execution behavior of program? %. That's very good. Which one is included in the other one? So formal semantic is the more broader way. Why do we need a methodology and notation for semantics? It's a multiple choice. Why do we need a methodology, guys? Or maybe we don't need one. I don't know. What do you guys think? These are good and important because, of course, in the midterm, sometimes it's not going to be just all solving problems. You're going to get some questions about understanding some things. Because you're third-year computer scientist, you need to know, for example, what's the difference between formal semantics and static semantics. Correct? Okay, it's definitely a good question, but also it's all of these three. Maybe we can detect ambiguities, of course. We say if you have the formal semantics in front of you, so you're going to check, is there ambiguity in here or not? So the three of them. Formal semantics assume that the syntax analyzer already filtered out all the syntax errors. Is this true or false? Hi, Philippe. For the people who arrived late, guys, I think there's maybe 3 people, so send me an email so I can add you to the bonus quiz. So I want everyone to answer, please, guys. We have 56, only 40 answered. So formal semantics, do we assume that the syntax analyzer already filtered out or no? In the formal semantics, we're actually checking for both syntax error and semantics error. Like, so both errors, or no, we're only focusing on semantic? It's actually true. Why? Who can remind me with this? What is the compiler formed from? Michael, how does it start the compiler?
There's this syntax analyzer and then the semantic.
Exactly. So the compiler, we start lexical analyzer, syntax analyzer, and then semantics. So the input to the semantics analyzer, for example, it's already coming out from the syntax. So if I'm writing my formal semantics, I'm going to write it in a way that I'm assuming all the syntax are correct. So please keep this in your mind. Now, can I replace this? X equal x plus 1, x equal x plus 1 with x equal x plus 2. Is this the correct optimization? Can I just replace them? Yes, no, or it depends? So if you're optimizing this code, what does it mean for you? It depends, actually, right? We said it depends what language. Some languages use parallelism, some other no. So you need to understand, you need to know the formal semantics of this or the language, and then you're going to be able. If you want to remember this, always remember, let's say some languages support mutability, some other language doesn't support mutability when it comes to memory variables. What are the different semantics approaches that we just mentioned in this class? Let's filter the people who are asleep. So that's very easy. We only mentioned 4, correct? So there's only 4 answers. I like how you always discuss the answers together. That's good. It means that you're a team player. Yes. Actually, if you're able to pass the interview, then actually if you're able to work in teams, that's the best thing. But to get past the interview, you need to depend on yourself. So We have operational, denotational, axiomatic, and then there's 21 said syntactic semantics. Only 2 said national semantics. Exactly, that's the wrong thing. If it was Canadian national, it would have worked. So of course, there's nothing called syntactic semantics, because syntactic mean syntax, semantics mean meaning, but there's something called static semantics, which has nothing to do with these. So the approaches that we saw on the slides are 3: operational, denotational, axiomatic. We said we're going to focus on the axiomatic.
She got static semantics.
Match the definitions. Which one it explains how a program state changes step by step? And which one talks about the pre and post condition? And which one is solidly based on function? Of course, operational is step by step, denotational always functions. That's how I want you to link these. And then axiomatic is pre-post conditions. Describing the operational semantics of high-level language statements requires the construction of either a real machine, pure interpreter, or a virtual machine, idealized machine. Which approach is better? Pure interpreter, idealized machine, virtual machine? Which approaches are better? Exactly. Both of them are the same, guys. Of course. Pure interpreter, we said it's not good idea. Why? Who can remind me why it's not a good idea to have just a pure interpreter? Catherine. It's going to be, when you're describing your semantics, you're going to also describe the hardware specification without meaning to it. So it's going to be more related to a hardware or operating system specific thing. Now, what are the steps of the idealized machine approach? First, translate the source code into machine code for the idealized machine. First, translate the code from the written language into a source code. Then we execute the code on ideal machine bought from Apple, or we want to execute the code on ideal machine with a stable CPU. And then we want to simulate the code on a virtual machine, simulate the code on Windows, Linux, or a Mac. What are the steps? So here we have translate the source code into machine code for the idealized machine. Translate the code from the written language into a source code. Execute the ideal machine with a stable CPU. Why not GPU? Why you chose CPU? You don't have a gaming PC at home with the GPU, so you decided I'm going to stick with the CPU. If you're using machine learning, what's going to happen to you if you don't have a GPU? It's not going to work, right? So of course, it's not going to be an ideal machine with a stable CPU. It's going to be a virtual machine. Why? Because ideal machine means virtual machine. Correct? When we mention idealized machine, we're talking about a virtual machine, that it's ideal in the abstract. Of course, these two. Okay, guys? For which language paradigm the denotational semantics is mainly used? Imperative, functional, logical. Of course, functional, because it's based on functions. So now let's go back to axiomatic assertions. So axiomatic semantics, guys, is based on mathematical logic. So this logic expression are called assertions. So whenever we say we're basing things on assertions, that means we're basing it on logical expressions. Okay, that means what? Like, for example, when x is greater than 0, this is an assertion for me. Okay? An assertion is a logical statement that expresses something about the state of a program at a particular point in its execution. Assertion can be true or false. Don't worry about this. We're going to actually explain every single thing with an example, so it will be less boring for you. So what are the types of assertions? We mentioned them. Axiomatic semantics has two types of assertion, pre and post. So precondition can mean what? For example, I'm saying my precondition is that x is greater than 0. So I cannot execute, or to be able to execute this statement, x has to be greater than 0 for this statement to work. Or postcondition, that means after the execution of the statement, it has to be y equal yx of 1. So do we understand the difference between precondition and postcondition? So the postcondition is after I executed the line of code, I'm expecting this line to always have y equal yx plus 1. Precondition is before executed. Let's leave the questions because you're going to understand them with the examples, because I'm running out of time. But then if you don't understand them, then we'll answer the question. Let's take this one. So if you see something like this, sum equal 2 times x plus 1, and then we have this. This, if I'm telling you what is the assignment statement, this is the assignment statement. Okay? What is the post condition? Is this one. Okay, guys? You're understanding this. Now, you need to reason about these. So what do we mean by reason? We're going to look at this. What does this statement mean? It means that the sum is going to be depending on the x, correct? And then what is the post condition means? That after the execution of this, I'm expecting my code to have sum greater than 1. That means if I try this, and doesn't give me sum greater than 1, I know that it didn't follow the semantics. That means the semantics are wrong. That means this code is not correct. Yes?
Doesn't always have to have a precondition and a postcondition.
We're going to see it. So we're going to step by step work. It means that after sum equal 2 times x plus 1, we expect the value of sum to be greater than 1, correct? And the reasoning, in order for this sum to be greater than 1, what do we need? A precondition. So how can I guarantee this postcondition? I need to also have a precondition. In this case, if you look at this one, how can I know when sum will be greater than 1? Give me an example. Yes.
This is greater than 0.
For example, if x is greater than 0, it will work. If x is equal to 2, it's going to work. If x is greater than 10, would it work? So 2 times 10 plus 1 is what? 21. It's going to work. So for example, if I have x is greater than 0, so I can say a precondition for this is x greater than 10, for example. It will work. Now, what is the problem with this answer that I gave? There is no problem, but it's not perfect. There may be a bit of ambiguity about it. That's why we need always better for us to have weakest precondition. The weakest precondition means the least restrictive condition. Because we said, okay, x greater than 10 will work. X greater than 5 will work. X greater than 2 will work. What is the tightest one? That's what your friend here said, x greater than 0. So this is my tightest or the least restrictive condition. So that means it's called the weakest precondition. Okay? Because as you can see here, all of this will work. Then the weakest precondition is x. Now, if you have a program, guys, be careful on this. If I have a program that this is the post condition and this is the precondition, and I'm telling you, is this program correct? What's your answer? Who says yes? Who says no? It's yes, guys. It doesn't have to have the weakest precondition if I'm asking, but if I'm telling you the weakest precondition is x greater than 1000, you're going to tell me no. Very good. So let's solve these things together, guys. Because I don't trust you anymore to not fall asleep. So we're going to go do another. We're going to solve them together. Let's solve these three questions together so we can understand a bit more what do you mean by post-condition, precondition. And I want everyone to try to solve it either on their iPad or their pen and paper. That's how we want to practice.
Professor,
Yes,
question from earlier.
go ahead. Yes, sorry, I forgot to ask.
Post conditions always language defined or can they be reviewed?
No, language defined. Because here we're talking about you're designing a language. You didn't even give it to the user yet. Okay. Okay, we're ready. So what is the weakest precondition of this? A equal B divided by 2 minus 1. And then my post condition is A less than 10. So let's say I'm asking you this question. I'm giving you this, and I'm giving you a post condition. How can you reason about what is the weakest precondition? Try to think about it a bit and choose one of the answers. And then we're going to reason together. So you need to find a precondition that will allow you to what? To end up with A less than 10. But here, we want the weakest precondition. Not like any precondition that will work. Give you another minute. Okay. So we have B less than 22, B less than 4.5, B less than 11. Okay. So let's start from top to down, or from top to down. So B less than 22, who said it? Who wants to explain why? What's the reasoning behind it? We'll start with him. Yes.
If you plug in 22 in that, like in your equation, b over 2 minus 1, you get b equals to 11. Or yeah, 11 over 2 minus 1. So it comes to 10. So a wouldn't be 10 wouldn't be less than 10, but like the lowest one that would fail.
Okay, so you substitute 22 by B. So you said 22 divided by 2 is what? It's 11 minus 10. So that's giving me A equal 10. But it's going to give me A equal 10. Yeah, so you're saying less than 22. Okay. Any other reasoning about why you chose B less than 22, Benjamin?
I sort of did the same thing, but instead of that, I just solved the inequality. So I put b over 22 minus 1 less than 10 and just solved it.
Okay, so the same idea, but you solved it differently. Samuel, you had the same thing. Okay, who said B less than 4.5? Who wants to explain why? Who said B less than 11? Okay. So B less than 22. Okay. Why it's B less than 22? Can you see? Oh, you can't see it. Okay. So look here, guys. That's not the same one. Okay. So let's continue the book lab and then we'll go here. Can you see the book lab? No? Okay. Okay, let's continue the book lab. Now the other one. What is the weakest precondition of x equal 2 times y minus 3? Again, guys, I need to find something that will end up with x greater than 25. We'll take just one more minute and then we'll go back to the answer is not there. So let's go with 11 for now. And let's just stop now this. And I want everyone to focus with me now so we can solve this before the time ends. Okay, so let's look at this, guys. Here, I want to reason about this. So how do I reason? I left for you like, step-by-step things if you want to go back and read them. But for us, I have Z plus 1 here. Correct? And I want to end up with Z less or equal than N. In this case, what can I say? Z less or equal than N minus 1. Would this satisfy this? Okay, so what is the formal way to do it? It's like Benjamin said in the beginning, that's the best way. Is actually, I have Z here, I have Z here. Correct? So I'm going to replace this Z by this. I say Z plus 1, for example, less or equal than N. So Z is less or equal than N minus 1. So that's the easiest way usually to get the weakest precondition. Even though if I write, let's say, Z N minus 2 or minus 3 is going to work. So let's go and try to solve this one. This one here, let's solve it just by reasoning it. If I have the precondition and I want to deduce the postcondition, what can I say? If I'm saying A equal A minus B, and A is going to always be greater than B. So A is always going to be A greater than B. So what would happen? What would be the postcondition always, Michael?
It would be greater than 0.
Exactly. It's going to always be positive. So that's the reasoning here, right? So we're going to end up with it. So what are we seeing here? Sometimes you're going to have the precondition to deduce the postcondition, but the majority of the time will give you the postcondition to come up with the weakest precondition. And some other times we're going to give you both precondition and postcondition and just ask you, is this correct statement or not? Okay. So the assignment statement, it should always look like this. P represent the precondition, Q represent the postcondition, and then we'll have the statement. So whenever we see these brackets before the statements, that means this is the precondition. I don't have to tell you that this is precondition because always the one before the statement is the precondition. And then always we're going to assume X equal E. What do we mean by that? For me to find the precondition, I'm going to use this precondition equal postcondition when X equal to E. What do we mean? Let's look at this, guys. In this case here, X is what? A. E is E. So I'm going to say, I want to replace X by E. So I'm going to replace this by, this by this. So if I replace it, B over 2 minus 1 less than 10. Then I'm going to say B over 2 less than 10 plus 1. Then I'll take this here. So we'll end up with what? 22. So B is less than 22. That's why we had the weakest precondition B. So that's actually mathematically how you were going to solve it. And you just did. So let's take the next one. So this one, guys, how are we going to solve this? I want to replace X by this one. How can we do that? 2y minus 3 greater than what? 25. I'm just basic math, correct? So 2y greater than 22, y greater than 11. That's why it is 11.
3 on both sides.
Yeah, exactly, 28. That's true.
5, 28, and then 14.
That's true, 14. It was not there. Very good. So 14. Okay, guys? So basic math, and we make mistakes in the basic math. Okay, so that's the answer. So this is the steps that you're going to do to find the weakest. Always remember, it may be, for example, other thing, but not the weakest. It's still correct. We're going to fix this. Now, x equal x plus y minus 3. What is the different thing that we're noticing here? And I want you to get, guys, please focus with me. Just 5 minutes and then you leave. X, we have x also here. So let's solve this together. Again, we just want to replace x by this. So if we do that, it's going to be what? X plus y minus 3 greater than 10. Correct? It's going to be x plus y greater than 13. How should I continue after that? Should I say x is greater than 13 minus y, or should I say y is greater than 13 minus x? Which one I should say? Samuel.
Go for the first one, x, because it just matches the post condition, but I think they're both equivalent.
Exactly, guys. So all of these are describing the same relationship, so it doesn't matter. Okay, so that's why don't get confused if you see x and y here. Any of these is the same thing. We're just like rearranging them. So any of these answers are fine. Now, again, yes, Benjamin.
Once we have the x plus y greater than 13, should we then replace our x with 10 because we?
No, this is the precondition. You're just saying you're going to put, I have to have x plus y greater than 13 to be able to end up with the post condition. Okay, did you get my point?
Because it's a different x at the end.
Yeah. So there's old and new x. Now, the idea of the axiom, we're going to call it axiom, right? This is a proof of correctness. If I'm telling you to prove if this is correct, I have to give you the precondition and the postcondition. Both of them I have to give you to be able to prove if this is correct or not, right? So in this case here, I gave you x is greater than 3, x is greater than 0. So how can you prove this is correct? You do the same exact thing, but you need to end up with x greater than 3. You know what I mean? So if I give you them both, you're going to do the same thing. So replace x by x, it's going to be x minus 3 greater than 0. That means x is going to be greater than 3. Is this the same as this? Yes, that means, yeah, this is correct. Okay, now what will happen if I change x greater than 3 by x greater than 5? Is this still correct?
Yes,
I want new faces, yes?
it is correct.
Why?
It's not the weakest, but it does.
It will still work, right? Because if I continue doing this, I'll end up with what? X greater than 3. Now, if you look at this and look at that, by consequence, what will happen? Yes, I can say x greater than 5 applies also as x greater than 3 is going to also still be correct, even though it's not the weakest, but it will be correct. So this is called the rule of consequence. Okay, so there will be more than one rule to be able to solve this. Now, another rule, guys, so that's why I gave you this example, so you don't have to look at this and freak out, okay? So this is just for you to understand these formal rules in the book. But the idea here is that if you proved, if you have this is going to be, yes, Benjamin.
You know, should be reversed. You say, however, it's obvious that x greater than 5 implies x greater than 3. It should be
Exactly. Okay, I'll fix these because I made these slides in the morning. Okay, now another rule will be rule of sequence. What do you mean by that? Sometimes you're going to have two sequence, like sequence of statements, not just one. You're going to have S1 and S2. What will happen in this case? Let's take this one. So I have two statements and I have one precondition, postcondition, and I want, let's say, to get the precondition for it. Or if I give you the precondition and you want to prove it, both will be the same thing. So how can I do that? How can I tackle it? The proper way to tackle this, you're going to start from the left statement. So let's solve this. Y plus 3 less than 10. What would be y less than 7? Correct? Can I say this is the precondition? Not yet. I didn't do it here. So now this will be the new postcondition of this statement. So I'm going to solve this statement with this postcondition. So now how can I solve this statement? I'm going to say 3x plus 1 less than 7, and then x will be what? Less than 6 over correct? And then now x less than 2 will be the precondition for both. So and this is called rule of sequences. So that's how I work. If I give you 5 sequences, you start with the last one always, not the first one, the last one, and you go backward. Okay, the last rule of selection. Rules of selection will work if I have if conditions in my language, because we say, okay, we can have the normal statement, then what if I have if condition? So I'm saying if x greater than 0, do this, and else y, do this. So I have one post condition. What do I do? In this case, I don't start with the last one because they have an if condition. I'll apply this post condition to both. Okay, so what will happen? The first one is going to be y greater than 1, and then do the same thing is going to be y greater than -1. So which one I should choose? Which one covers both? Y greater than 1, y greater than -1. Y greater than 1 will cover both. So I'm going to choose this to cover both of them. Yes.
Could we also include x here to cover both cases? So
I-
x greater than y and x positive or
I can't do this because I have to follow the post condition. Post condition is talking about y. So the only thing I can do is I replace y by something. If there was x inside the y, then maybe. Let's say here it was y equal x minus 1, then it will be. So we just have to follow the precondition. I can only replace this part, the left part, by the right part. If there is no x here, I cannot mention anything about x. Okay, guys, then we will have the logical pretest loops. Now, so we covered sequence, F condition, now we need to go into the loops. It will take some time, we'll cover it on Friday. Okay, guys, good? Thank you so much. Just a second.